learners, welcome to section 6 of unit 6 in the course Introduction to Abstract Algebra. So actually this will be our final session of both unit 6 and also the entire module titled Introduction to Abstract Algebra. We are going to devote our time here to talk more about fields, and I'm sure you will like it and it's very interesting. I am Unkaila Dasmani, your course instructor. By the end of this session, you should be able to explain what a field is, give at least 2 examples of fields, state and prove at least 2 properties of fields, also solve simple algebra problems in integers, and that's where n is a prime number or prime. So prime number is an integers modulo n, so integers modulo n. Okay, definition of fields. A field is an algebraic structure which incorporates one set with 2 binary operations. I've already mentioned that in the previous video. Let's look at definition 9. A field is a set F together with 2 binary operations, and that is plus and then dot multiplication that satisfy the following axioms. So you're looking at definition 9, and the following axioms must also be satisfied. The first one, the addition is associative. Axiom 1 and the third F1, the addition is associative. And you know that once addition is associative, and then you can actually write, you can write all like what we're doing for the group and the rest. So addition is associative, so I can write A plus B plus C equals 2 A plus B, that's A plus B, okay, plus C. Here you can say that for all A, B, and C be a member of the field F. We can also talk about commutativity. A plus B is equal to B plus A. And then here we are talking about addition. If we talk about the multiplication section, if I want to have the multiplication section, I will say A dot B equals to B dot A. Okay, and that is for all A and B being a member of the F. So that is addition hold. Here is the addition hold. The addition is here, and then the commutative is here. Okay, and the same happen here, cause additive. So F3 we've already gone through that. F4 we've done that. So you can go through up to 6 and write them. They are very, very interesting. I'm sure multiplication is commutative. F6, I've already done that one where I say A dot B equals to B dot A, and then A and B are all members of the field F. So go through and then look at the rest. Very interesting. We have 7, 8, and 9. So I'm sure you have already gone through something like that, so you can easily do this one. Example 11. The set R of real numbers forms a field under the usual operation of addition and multiplication. How? Also, the set Q of rational numbers forms a field under the usual operations of addition and multiplication. Explain that. Also, the complex numbers and addition and multiplication. Just explain with yourself. Okay, that's a repetition. Algebra of fields. So the element of field or a field satisfy exactly the same algebraic axiom as the set of real numbers. For this reading, or for this reason, elementary and basic linear algebra for the set of real numbers translates directly to algebra for the element of a field. Since the definition of a field involves only addition and multiplication, we define subtraction and division for element of a field. Okay, so as I have talked about that, so here we are going to look at subtraction and division. So you can find more exercises in your book. Do more. You can also find examples, different examples there, which are very, very interesting. Okay. So let's look at definition 10. As I said, we are looking at that. We are going to look at division and then subtraction. Suppose that F is a field, so we have A, B being a member of the field F, then the difference of A and B is defined as A different B. It's the same as A plus negative B. You can see very interesting. So here the negative B is the additive inverse of B. Also, if B is not equal to 0, then the quotient of A and B is defined by the formula. A divided B is the same as A on B. Same as A multiplied by B inverse, that B1 on B. Note that 1 on B equals to B to the power negative 1. Okay, so that becomes multiplicative inverse. Example 14, let's try to solve this equation. Solve the following equation. 3x plus 4 is congruent to 6 mod 7. So here what we do is that we try to solve for the addition and multiplication table for multiplication, addition multiplication table for modulo 7. So don't forget about the table, and we have them there. So we have the addition one here, first one is here, the multiplication here is here. So how do we then solve for this? So let's try to do it over here. So we have 3x plus 4 is congruent to 6 mod 7. Okay, so here, first place we can take away the 4 by subtracting 4 from both sides. So I get 3x is congruent to 2 mod 7, and I hope you agree to me with that. Okay, so next what we do is that we are going to divide through by 3, and we said that if you remember, if you want to divide through by 3, what do you do? Divide through by 3 is the same as 3 with the power negative 1 times both sides. So when you multiply 3 with the power negative 1 by both sides, it's like we dividing through by 3. So if you want to do that case, let me try something here. So in that case, we can see that we want to see if we can get 3 with the power negative 1. So dividing both sides is the same as multiply both sides by 3 with the power negative 1. And I hope you agree with me. So I can make this one from the multiplication that 3.5. What do I get? 3.5 is actually equal to 1. So from here, if I divide through by 3, so 3 to the power negative 1, same as 1 on 3. I hope you agree to me. It means that 3.5 equals to 1. So I can say that 5 equals to 1 on 3. Therefore, 3 to the power negative 1 is same as 5. And this one is under the multiplication modulo 7. So having established that, it means that where I'm dividing by 3 exponent 1. Therefore, I can actually represent it as 3.5, because 3.5 is actually giving me the same result. So I can say that 3.5x equals to 2.5 mod 7. Okay. What do I get? So you can see that x is actually equals to 3.5 is 1. So let me write this x first, correct? 3.5 is 1. So let me write this, clean this one. So 3.5 is 1. Left is x. X is actually congruent to 2.5. And 2.5 is what? 2.5 is also congruent to, you go to your table, 2.5 is also, let me use that one with different marker. 2.5 is given by 3, so I get 3 mod 7. Let me clean this one. Okay, so I get 3 mod 7. So that's actually solve this question. So simple. So you can do a lot. Then example 15 in your course book, you can solve that example and then make use of the same idea. You can play around that. So this ends the course Introduction to Abstract Algebra. Thank you for your time. It has been not easy for going through from it 1, session 1, 2, with 6, section 6, actually 36 sections. Yes, I'll say thank you and congratulations for devoting your time to read Introduction to Abstract Algebra.